Hi there, my name is Charles Sipa. Welcome to another presentation of differentiation. This time we're focusing on the differentiation of trigonometric functions. I think everybody by now you know what are trigonometric functions. For example, these are trigonometric functions. We start from sine. I hope you know that sine is actually the parent function for all the trigonometric functions. Sine, we know it's defined from the beginning when we were dealing with the right angle trigonometry, and now we can define general. And then cosine is the sine of the complementary angle. Then tan is the ratio of these two, and the rest actually are variants of just manipulating the basic trigonometric functions. So now, to differentiate trigonometric functions or differentiation in general, I would like you to understand the structure of the function this way. Any function, in this case I've taken trigonometric function as an example, I think it's got the following structure. We've got the independent variable, in this case which we say here is y, because remember, we plot our functions on the system of coordinates x, y. And when we get a graph of a function, any point there is equal to x, y, and the y is actually equal to f of x. So then we say that y is the dependent variable. And then x, as we see it here, is the independent variable. But in addition to that, looking at x here, its position with respect to the function y, or in this case function cosine, we are going to call x, of course it's independent variable, we're also going to call it the argument of the function. And then now cosine and the sine, those are just names of the function, and the name also might indicate the type of function you're dealing with. So as long as you're dealing with cosine and sine, we know we're dealing with trigonometric functions. And then y, we've said here, is just a function. Of course, y is a function. The name might change, you might get to exponential or power function and so on. And then looking at x here and this x squared there, both of them collectively, we're going to call them argument of the function. So when you are differentiating, I think it's very important to know which is the immediate function you're differentiating. For example, here, the function of differentiation is sine, and there the function we would be differentiating is cosine. So our cosine here is our immediate function, but here our sine is a immediate function, and the x squared is also a function, but is a function as an argument of sine. It's very important to understand the hierarchy in order to differentiate accurately. So now let's move on and now derive the derivative of cosine using the definition. We remember that the derivative of function using the definition was defined by the limit of the incremental quotient as delta x, the change in x, is tending to 0. So what we're going to have, we are going to have cosine x plus delta x minus cosine x over delta x. So I'll remind you here that now, at this stage, you need to recall your trig identities because they're going to be handy in simplifying some of these calculations. So now we're going to have your limit as delta x is going to 0. I hope you remember the identity I'm going to apply here. This is going to reduce to cos x, cos delta x minus sine x, sine delta x minus cosine x. If you don't remember, don't feel bad. Just take your time and try to remind yourself a number of trig identities because they're going to be useful in this case. Now, looking at this limit, we know that as delta x is tending to 0, cos here will tend to 1. So the expression here is almost equal to the expression there. They're not exactly equal, but the difference is not much as this is tending to 1. So for that reason, we're going to simplify that this way. Then we're left with limit as delta x is approaching 0 of minus sine x multiplied by sine delta x over delta x. So now, if you look at this expression, you'll notice that we've got here sine delta x over delta x, and we're calculating the limit here as delta is going to zero, so which means we've got our special limit which is discussed before, and we know that this limit is equals to 1. So therefore the result of this limit will finally be minus sine x. So we'll finish our calculation. What we're actually saying here is that the derivative, which you can denote this way, of cosine of x, so cosine of x prime is equal to minus sine, or we can denote it also this way as d dx. In this case here, d dx is a differential operator, so we're saying here we're differentiating cosine x, and the answer will be minus sine x. I hope that is understood. I'm not going to give an example for this one here, but I'll urge you to practice this and remember this. This is the explanation here, just to make you understand why the derivative is that. So you don't just take it as a formula which comes from something which you can call mathematics. This is mathematics. Okay, so now let's come to this one. And this derivative, if we compute it via the definition, it is actually going to be more revealing than just to say derivative of cosine of x with respect to x is equals to minus sine. This problem, as we have seen it, is not very revealing exactly what happens when we're differentiating, and this one will be more revealing. So let's start there. What's going to happen now is we're calculating dy dx by the definition. We know that this is limit as delta x is going to 0 of this case of sine x plus the delta x all squared minus sine x squared all over delta x. Obviously, see here there's some kind of tedious calculation you need to do here, but we're going to bear with that because there's a very important illustration which I want to show you here so that you can understand the differentiation very, very clearly. So this expression is going to be x squared plus 2x delta x plus delta x all squared. So for now, we're going to pause a bit here and try to work out this expression to its simplest form, then we'll bring it back to this problem. We're going to have sine of x squared plus 2 delta x times x. So we're going to have sine x squared plus 2x multiplied by delta x plus delta x squared, all that in brackets. I think you're going to excuse the peacock outside, but I hope it's going to form part of your entertainment as you listen to this long explanation. Now what's going to happen here, let's group these two things this way. Let's say we group this as B and group that as A. So we're going to have here sine of A, which is x squared, sine of 2x delta x plus delta x all squared plus, sorry, there's a mistake here. This is supposed to be sine x squared cos that plus cos x squared sine 2x delta x plus delta x squared, all that in brackets. So this is quite a long calculation, but bear with it. So now when we get here, we need to simplify that and we need to simplify that. So now what we're going to have here is we're going to have sine x squared cos 2 x delta x cos delta x squared minus sine x squared, sine is multiplying this part and multiplying the next part, sine x squared sine 2x delta x by sine delta x all squared, plus here we're going to have cos x squared multiplied by sine multiplied by cos delta x all squared, plus last term will be cosine x squared multiplied by sine of delta x squared cosine 2x delta x. So now what I'm going to do here, I'm going to try to simplify some terms. Now that we're going to have sine, we have to calculate sine delta x, sine x plus delta x all squared minus sine x, which means from this expression we must subtract minus sine x, not sine x squared. If at the end of this row we subtract sine x squared, let's see what's going to happen. Note that here the argument of cosine here is very small. It's actually delta x squared, which is actually smaller than delta, and here we've got delta x cos that. So these two cosines here are going to approach 1, 1. In that case, this part and that are going to simplify. So we're going to be left with, we're going to be left with this term, this one, and that. Now it's 3 terms. So let's see what that gives us. Now let's write this here as minus sine x squared sine 2x delta x sine delta x squared, and this term also I think we can quickly simplify it very easily. So but let's not do that for now. Let's leave it there as cosine squared sine 2 x delta x cosine delta x squared plus this one, which is cosine. This is the one actually which we can simplify very easily. Look here, sine is sine delta x squared, and this one is cos of 2x delta x, which we expect to approach 1 as delta is going to 0, and this one is sine of something which is even smaller than delta x, and so this one approaches 1, and this one is going to approach 0 because it's delta x squared is even smaller than delta x, so it's going to go fast to 0. So we can simplify this expression and say it all tends to 0. So we're left with these two expressions. Now what we're going to do now, we're going to take this expression to that part and divide it by delta x. Let's do it this way. What we've got from this calculation of this difference here, we're left with these two terms, this one and this one. Then next we're going to divide the 2 by delta x like we've got here. So what we've got is the following: dividing that by delta x, which gives us that, and those two expressions get us to that. But actually we're actually supposed to be left with one term here. Let's informal again analyze what's happening here. What you've got minus sine x squared sine 2x delta x, and you can see that as delta is going to 0, this argument is going to 0, and this one is delta is actual times here, not plus, delta x squared, which is even smaller than 0. So which actually means that this whole term, this is going to tend to 0 faster than this one, but then the whole term here is going to tend to 0. So finally we're left with one term, which is this one. Let's see what it gives us. So we've got limit there as delta x approaches 0 of cos x squared sine 2x delta x multiplied by cosine delta x squared divided by delta x. Again here, I think you can see that delta x here is squared and delta x tends to 0. So which means this one will approach 1. And essentially here what we're left with limit delta x going to 0 of cos x squared sine 2x delta x all over delta x. Now at this point you can see that cos here does not depend on delta x. So what you can do, you can use the properties of limit and take it outside the limit, and you've got the following. You can write this as cos x squared multiplied by the limit as delta x is going to 0 of sine 2x delta x all over delta x. When you get to this point now and you want to conclude this kind of calculation, you notice one thing, that here what we have is similar to our special limit, which is limit as x going to 0 of sine x over x, which is equals to 1. But this is not the exact situation. What is the difference here? Note that here we've got sine 2x delta x, and here delta x and then delta x. In other words, the behavior of x there as an argument of sine is not the same as x there and there. So to achieve that kind of situation, in order to conclude this, we need to accelerate this by 2x there and there multiplied by 2x, which essentially we're multiplying by 1. So we can change the value of this rational expression. So having done that, also we can accelerate here 2 by 2x. Then in that way, we've managed to get this situation of this limit. Then you can rewrite this as cos x squared multiplied by, notice that 2x here does not depend on delta x, so multiplied by 2x. Now you're taking 2x out of the limit, multiplied by the limit as 2x delta x goes to 0 of sine 2x delta x over 2x delta x. So we know that this limit is equals to 1. So what we're concluding this, we're going to write derivative of sine x squared with respect to x will be equals to cosine x squared multiplied by 2x multiplied by 1. I'm writing this like this clearly so that you can understand what I'm going to say next. So remember at the beginning I said when we did the derivative of cos x, which gives us minus sine x, I said it was not really revealing exactly what's happening with that differentiation. So in this case here, what we're going to say is we're going to conclude that cosine is the immediate derivative of sine. Cosine is the immediate derivative of sine. And then the derivative of this function with an argument x squared is going to be cosine returning the same argument multiplied by the derivative of the argument. As you can see here, 2x is the derivative of x squared with respect to x, which is going to come as 2x multiplied by 1. And the 1 here, we can actually take 1 as equal to dx over dx, which is actually now the derivative of the argument of this power function here, which is x to the power, here the function is x is power 2, so the argument is x. Then you can look at this as the derivative of the argument of this power function, which is here. So what I'm trying to emphasize is that whenever you are differentiating a function, you first of all call upon the derivative of the immediate function. By immediate function, in this case, you saw that the function was y is equal to sine. So the immediate function is sine, and this argument is x squared. So you call up, first of all, you call upon the derivative of the immediate function, and then secondly, you multiply by the derivative argument, and that argument could be another function that we've got here is a square function. Then you multiply by the derivative of that argument. In this case here, it takes you to the simplest derivative, which is dx. So now, I think now you've got to put this in your system as some kind of slogan for differentiation. Whenever we are differentiating, we call upon the derivative of the immediate function multiplied by the derivative of the argument until we get to the simplest argument, which is in this case dx. But normally we don't write this, and sometimes people don't even talk about it. I talk about it because I think it puts the message very, very clearly. And I'm not accusing anybody for not talking about it, because in Spanish they say cada maestro tiene su librito, meaning each teacher has got his or her own booklet. So I'm doing this according to my booklet. So I hope now you can see how this reveals the whole process of differentiation until you are differentiating the simplest argument x, though we don't normally write this explicitly, and in most cases people presenting this might not talk about this. I'm not accusing anyone or blaming anyone for not talking about this thing. In Spanish we believe that cada maestro tiene su librito, meaning each and every teacher has got his or her booklet, and according to me, this is in my booklet because I think it passes the message very clearly how the process of differentiation is supposed to be done. At this point, I would like you to note that I don't have the time to do all the derivatives of trigonometric functions via the first principle. So what I'm going to do now, I'm going to take you to the standard table of derivatives of trigonometric functions. As you can see here, we've got the derivative of sine being cos, which we saw before, but according to what we have just said, it will mean that here there's derivative of x with respect to x. So now, if now the argument of the function is not x, then you can note that function as u. In this case, it could be a certain function u of x. In this case, we don't mind what this u of x is. It could be a polynomial, could be an exponential function, could be another trigonometric function. So what are we going to do? When we differentiate sine, we're going to call upon the immediate derivative of sine, which is cos, and retain the argument. Now, as we keep the same argument, then multiply by the derivative of argument with respect to x, because we said here u is a function of x. In other words, whenever you're given a function, you must try to monitor that in the final analysis, what is the independent variable of the function. So at this point, I'll urge you to learn these derivatives and do practice according to the exercise you've got in your text. I would like to apologize for the noise of the peacock outside, hoping that it also served as some kind of entertainment as you're listening to this long explanation of the derivatives. Otherwise, thank you for listening.